Okay, so this is our second video. We just finished talking about inulin, and now we're going to talk about PAH, or para-aminohippuric acid. So one more quick thing that I forgot to mention on inulin is I showed you that the glomerular filtration rate is here, and that it's 100. But I forgot to show you how to calculate it. So the GFR is the clearance, only for inulin. So if you take the clearance formula is the concentration of the urine times the volume of the urine divided by the concentration of the plasma. So let's find that in the picture. So the concentration of the urine is 1. The concentration of the urine is 100. The volume of the urine is 1. So that's 100 times 1 divided by the concentration of the plasma, which is 1. So 100 times 1 over 1 is 100. That's why this box here is 100. And only when it's inulin does this work out where the clearance that we just calculated is equal to the GFR, because it's 100. So if you are using inulin, you can fill this out, calculate the clearance, and then the clearance is the GFR. So why do we use inulin and its close friend creatinine? Just to get our clearance, because we want our GFR. That's our goal. That's how we get there. Now with PAH, we have a slightly different goal. We're still going to try and calculate the clearance at the end, but clearance for PAH doesn't give us the glomerular filtration rate. It gives us renal plasma flow. So that's the main reason we talk about PAH. PAH behaves differently than inulin, and we use it just because we can calculate renal plasma flow. We cannot calculate GFR. So you have to remember PAH, the clearance gives us renal plasma flow, and inulin or creatinine almost, the clearance gives us GFR. So let's look at PAH. PAH, we start with some different numbers. We're given 50, 500, 100, 0.1, and 1. So if we look at it, in the afferent arteriole, we have a 50 amount. So this is how much of the compound we have in milligrams. So we have 50. The water is the same. We're pretending this is the same kidney. We have the same amount of fluid. We still have 500 milliliters, but we have less of the compound. So it's less concentrated. We have a 0.1 concentration. Over here with inulin, we had an equal concentration of 1 to 1, but this is less. We only have 50. But we're still going to be filtering 20%. So if we look here on the calculator, we're going to filter 20% of 50. So 50 times 0.2 is 10. So we're going to get 10 filtered out here because we're going to filter 20%. And that's still pretty standard for this kidney that works correctly. If we take out 10 here, 50 went in, we took out 10, how much comes out in the EFF bucket? Well, 40. We took out 10 from 50, so we have 40 left. Now here's where it gets tricky. For PAH, the trick is every bit of PAH gets secreted. It's completely secreted. So even though we had 40 left over here in PC, nope, it all goes into the tubule. None of it stays in the blood, it all goes in the tubule. So P3 actually ends up getting all of it. So it's kind of weird. We had 50, we took 10 out, left 40 in, we have got 10, 10, 10, but now all of it here, the 40, all gets dumped back in, completely secreted, which means the peritubular capillaries are left with nothing. It all got secreted. And down here to the renal vein, we've still got nothing. None of it was resorbed. So in the urine, what do we end up with? All of it. So this is the special part, or the special characteristic of PAH. All of it gets secreted. Whatever came in here at the afferent arteriole, all ends up in the urine. So that's very helpful when we're calculating things later. Now, the flow, the water, is pretty much the same as we had before. We have 500 milliliters of water coming in. We filtered out 20%, and the concentration is the same because we haven't done anything to the concentration of water yet. So we've still got concentration of pH in water is 0.1. Here at the efferent arteriole, we took out 100, so we've got 400 left. Same as before. We came in with 500, took out 100, we've got 400 left. Now, in the proximal convoluted tubule, the P3 bucket, what do? Well, 100 came in Bowman space, is headed towards here, but just like before, we resorb 66%, so we've only got 33 left for water. And the convoluted tube, the peritubular capillaries here resorbed it. So the 2/3 left here ended up in here. So we've only got 33. That means 67 went somewhere else. It went to join the 400. So this is 467. And also with inulin, like before, we end up with only 1 milliliter of water coming out here, which means the other 499 had to be resorbed into the peritubular capillaries at some point before it gets to the renal vein, and so the renal vein has all of it. So if the renal vein... Okay, we had a little technical difficulty, so this is already filled in, but we're going to go and pick up where we left off. We're doing the 499 here, and so I just explained that when you have all of the 499 ending up here, you can tell because you only have 1 coming out the urine. So if 1's in the urine, you started with 500, all 499 have to end up in the renal vein. So let's do the concentrations really quickly. We were given 0.1 concentration here because we have 50 PAH coming in the afferent arteriole, but we have a flow of 500. So there's a lot more fluid compared to the chemical we're looking at. So we have a 0.1 concentration. And we're not doing anything to change the concentration in the Bowman space. We're just taking 20% of the fluid and 20% of the drug, or the compound. So we're still at a 0.1 concentration, and we already have it written in. Also, what we didn't filter in Bowman space, the other 80% that went to the efferent arteriole, it's the same concentration. 40, we took 10 out, 40 left. 400, we took 100 out, so 400 left. Same concentration, 0.1. So all three here, we 100% came in, 20% went here, 80% went here, but it's all the same concentration of 0.1. But it changes when we get to P3, because all of P3, all the inulin that was in the peritubular capillaries was secreted into the proximal tubule, so all of it's in there, 50, but at the same time we resorbed 2/3 of the water. So the 100 water turned into 33 water, the 2/3 went into the peritubular capillary, and at the same time all of this 40 went back into the proximal tubule. So our concentration is very different. 500 amount milligrams in 33 milliliters. So, or sorry, 50, not 500. So 50 divided by 33, we've got our 1.51 new concentration, much higher because all of it is in the tubules now. How much is left in the efferent arteriole and on the way to the renal vein? None of it. The peritubular capillaries have 0, the renal vein has 0. So what's our concentration here? 0. It doesn't matter how much fluid we have. We had 499 by the time we get up to here, but we have 0 of the compound, so our concentration is 0. But the urine is the opposite. All of it, all 50, we first got 10, and then the other 40 was secreted. All 50 made it into the urine, but we resorbed all the water except 1 milliliter, so our concentration is 50 divided by 1 is 50. So let's look here, TF to P ratio, like earlier, it should be tubular fluid to P, which is the plasma, and I mentioned briefly that these black boxes are black because we can only calculate a tubular fluid to plasma ratio for tubules. The afferent arteriole is an artery. It's not one of the tubules of the nephron, so it's black. The efferent arteriole is an artery. It's not a tubule. It's black. The the peritubular capillaries are black because they're capillaries. They're not tubules. And the renal vein is a vein. It's not a tubule. Okay, so we had one more little technical difficulty, but we were just mentioning here for the TF to P ratio, all the black ones here are not tubules, so we'll ignore those. The first tubule here, the first empty box, is the Bowman space, and so Bowman space is the tubule for TF divided by P, and P is always the afferent arteriole, so TF 0.1 over P, 0.1, 0.1 over 0.1 is 1. All right, what's our next tubule? P3, proximal convoluted tubule. What's our concentration here? 1.51 is our concentration. That's our TF divided by P, which is 0.1. This is our two concentrations. This one divided by this one. If you get out your calculator, that'll be 15.1. And our last tubule, the collecting duct here, U, for where the urine comes out, that concentration is 50 divided by 0.1, that concentration, so this concentration divided by this concentration, this tubular fluid divided by this plasma, because afferent arteriole represents the plasma, 50 divided by 0.1 is 500. And the important thing here that we want to use PAH for is to calculate the clearance of PAH, because if we look at the clearance equation, it's the same thing as we got for the GFR with inulin, but we're not going to be using it to find the GFR, we're going to be using it to find renal plasma flow. So urine concentration is 50 times urine volume is 1 divided by plasma concentration of 0.1. That'll be 50 times 1 divided by 0.1. That'll give us 500. So that's what our renal plasma flow is, 500, because we took all of the PAH that came in and we secreted it completely. All of it came out in the urine in just 1 milliliter of fluid, and because we know the concentration in the blood, in the plasma, we can use that to calculate how much blood came in for renal plasma flow. But over here, that wouldn't work. Why? Because we didn't get all of the inulin coming out. We only got 20% coming out, because that 20% represents the amount that was the glomerular filtration rate, the amount that came out. And we're talking about the rate of the fluid, and so it's in milliliters, and we get 100 milliliters per minute coming out of the GFR. So that was the 20%. So the clearance for both of these, it's the same equation, but the clearance for PAH gives us renal plasma flow, and the clearance for glomerular filtration rate, the clearance for inulin gives us the glomerular filtration rate.